is the reasoning of duh. Okay, but this is the reasoning. When I say the reasoning of duh, if, and I told you a little bit about this, if the door says pull, you go in, you push it. If it says push, you go to pull it. If it says caution hot, you touch it. Wet paint, you got to touch it. It's all of that. It's like, well, duh, it said it, it says it, let's do it. So we're going to develop an understanding of inductive and deductive reasoning, conjectures, and counterexamples. Okay? We good? Let's move on. Let's have some fun. All right. 1, 2, 3. Okay. So what's the next thing in the pattern? It'd be a 4x4, and then a 5x5, and then a 6x6. Right? And if I move down a little bit, 1, and then I have 3 blocks here, and then I have 6. So the difference here, how many more blocks go from here to here? 2 more. How many more blocks go from here to here? 3. Is it 3? Sure? Okay. 3 more. So 2, then 3. So how many more blocks would be on the next one? 4 more. Okay. So, well, duh, it's kind of right there. It should be kind of simple. We're looking for patterns of things to take place. 1 circle, 3 circles, 6 circles. So we have 1, 3, 6. So I add 2, I add 3, I add 4. The next one would have 10. Okay? Take a look what we're doing. Add 2, add 3, add 4. Keep going, add 5. We'd be able to keep going with these, looking at just specific differences of it. Okay, so patterns are out there. We go to 2 to 4 to 6. The next one would be 8 circles. Adding 2 each time. Pretty simple. All right, so arithmetic and geometric sequences. Okay, arithmetic basically means we're adding or subtracting to get to the next one. And geometric means there's some sort of multiplication scale factor that's going to take place. Okay? So, plus 5. What's this one? Plus 5 plus this. Okay? That's arithmetic. Good? What about here? Times 2. Okay? Some of you might look at this and go, well, that goes up by 4. That goes by 8. That goes up by 16. So it's growing at a different rate. So this is geometric. Okay? Any idea on this one? Divide by 3. What do you think? So if you got to the next one, it would be 27. Then it goes to 9. And then it goes to 3. If you divide by 3? Geometric? Good? What do you think? Happy? Makes sense so far? Uh-oh. What do we do? Oh, that's all it is? Add 1.2. Add 1.2. Add 1.2. So what is it? Arithmetic? Uh-oh, fractions. It's the F word. Well, 1, 2, 3, 4, 5. 2, 3, 4, 5. Oh, yeah, it must be a pattern. Well, what's really taking place? How do I go from 1/3 to 2/3? How do I go to 2/3 to 3/4? How do I go to 3/4 to 5/4 to 5? 5/6. Any ideas? A little tougher. Might be easier to get a common denominator. So what's the smallest number that 2, 3, 4, 5, and 6 all have in common? Don't say 30, because 4 doesn't work. 60? Does 60 work? I like 60. So if I made all the denominators 60, I might be able to see a pattern. Okay, so what would this have to be? 30. What would this have to be? 40. What would this have to be? 45. What would this have to be? What times 5 gives me 60?
48.
48. Okay, what about this one? 50. Well, shoot, I want 10, 5. Oh, 10, 5, 3, 2. Pretty much guaranteed that this is not arithmetic. Is it geometric though? Might not be either of them. Go, man. Cupcake. Benny, where you at?
I'm right here.
Dude, this looks bad.
It's green, that means good.
And congratulations. It says, please meet your mom. You don't know your mom? You're going to meet her.
Wait.
Now, that'd be really awkward if you truly didn't know his mom and she truly hears it. Ben, do you know who your mom is?
I hope so.
Okay. So you're really not going to meet her, like, for the first time? Okay, good. Because sometimes I speak before I really think it through, and it might offend somebody. So Ben, if I offended you, get over it. All right. I'm going to put a big question mark with this one, because I don't know if it's geometric or arithmetic at this point, but perhaps we'll get to a point where we'll be able to define that. What about this one? From 1 to 1, there's a change of 0. From 1 to 2, there's a change of 1. From 2 to 3, there's a change of 1. 3 to 5, 2. 5 to 8, 3. 5. Wait a minute. No.
Whoa.
Yeah?
It's the number added with the previous number.
Number added with the previous. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus... That works. I like that. This is actually... Is that going to work? Nope, nope, nope. This one doesn't work. Because 3 factorials should be 6. So that one, I was thinking it might be factorials. So arithmetic, geometric, I don't know. Might not, it might be a neither. Inductive reasoning. Inductive reasoning. A process that includes looking for patterns and making conjectures. Okay? We look for a pattern. We were trying to make some sort of reasoning behind how we get to the next part of the sequence. Making decisions or conclusions based on several decisions. Okay, if you're going through that buffet line and you're watching like the 10 people in front of you all go, oh, look, gosh, you're not, ow, that's hot. You might have realized, I'm not going to touch it. Or you might be that person saying, hey, let's stick along with it, right? Excuse me. Okay, deciding the next number of the series. Okay, that's pretty simple. After noting that the school cafeteria serves mac and cheese on 3 Fridays. Dude, I like mac and cheese. Do they serve mac and cheese in our cafeteria? Dude, mac and cheese is like the bomb. You guys ever been to CC's Pizza? They have a mac and cheese pizza. It's like, dude. And some of you going, oh, that sounds gross. No, it's like amazing. It's almost as good as the Oreos that are brought in. Yeah, they got like all kinds of flavors. So, after noting that the school cafeteria serves mac and cheese on 3 Fridays, deciding that mac and cheese will be served this Friday, you might have a pretty good shot at it. Okay? All right, what else we got? The conjecture, unproven statement that is based on several observations. So if you have some number sequence that you just can't find a pattern to, there might not be a pattern to it. It might just be random arbitrary numbers. You know, after adding 3 plus 7 is 10, 5 plus 11 is 16, 1 plus 9 is 10. The conjecture could be the sum of 2 odd numbers would be even. Oh, wait a minute. Let's say that one more time. The sum of 2 odd numbers will be even. If I add 2 odd numbers together, do I always get an even? Well, there might be the one time you have some counterexample, but I don't know. Using inductive reasoning can lead to an incorrect conjecture. Okay? You guys all played the game Monopoly? You all might have realized that the game of Monopoly might take a little bit more than 10 minutes. It could take days, right? I mean, it's a long process. And it's always good to be the banker because you can skim off the top. You don't really go to jail for skimming off the top. And the only people catch you say, dude, you're cheating. Okay. But one thing that you might have started to realize with the game of Monopoly, the younger you are as a child, you might have thought, oh, I'm going to get Boardwalk and Park Place. Because the only mental conclusion you had going in your head is that has the highest amount of rent when you have the hotels. And then the two first purple ones, people are like, why do you even waste my time and money on those? Yeah, but hotels, but there is. So if your whole ambition when you're playing the game of Monopoly is to say, I just want the top two properties, I want Boardwalk and Park Place, you're probably not going to win the game. Now, is that true 100% of the time? No, you could theoretically win. I gotta sneeze, hang on. Excuse me. But, and why did you think that as a kid? That, you just looked at those two big properties, you saw the card going, dude, you land on Boardwalk with a hotel, that's $2,000. I think that's what the name is.
Yeah, but what are the odds?
What are the odds? It's always 50-50, right? You either will or won't land on it. Wait a minute, I don't think that's right. You're probably right. So if you came through and you started thinking, I will win this game if I have these two particular properties, you might realize that's not always the case. Especially if your whole game plan is, I'm never going to buy any properties. Why would I buy a railroad? Can't even put hotels on it. Okay? Why would I want one of the utility companies? Then they try and mess with you on Monopoly saying, if you have one property, they roll the dice and you multiply by a factor of 4 and that's the rent. But dude, if you have both properties, what's the factor you multiply by? 10. Okay, good. I'm glad you guys played Monopoly at least once in your lives. That's awesome. Is this a thing to move here? Oh, it's a peekaboo thing. Okay. All right, let's see. Find a pattern and then make a conjecture about what comes next. So I had the whole thing blue, then I had half blue, and then I had how much blue? Quarter. So I went from 1 whole to 2 halves to 4. What's the next? Do I have how many? 1/8? Oh, is this? Oh, yeah, look at that. Is that what we thought? I mean, I guess we could draw in, well, you're talking about an 1/8 and a 16th and a 32nd. So the more and more you go, the closer and closer and closer it gets. And never get there. It goes along with something called Fermat's theorem. But that's later in life. All right. Find a pattern, predict what's next. Number of sides, 3. Number of sides, 4. Number of sides, 5. Number of sides, 6. 7-sided object we don't have here yet. Number of diagonals, none. Number of diagonals, 2. Number of diagonals, 5. Number of diagonals, 9. So let's see. If I went from, let's go here, 2, 3, to 4, would you think that this would have 5 diagonals? Does that seem like it's logically making sense? I'm adding 2 each time. So let's try and draw a 7-sided object. I don't know. 1, 2, 3, 4, 5, 6, 7. And just to make me feel better, I'm going to put a dot at each of the vertices. 1, 2, 3, 4, 5, 6. Is that 7-sided? 1, 2, 3, 4, 5, 6, 7. Is that good? Feel okay? All right, yellow. There's a diagonal 1, and 2, and 3, and 4. Is that all right? How many do I have to get to? 14. So there's 4, 5, 6, 7, 8. Come here. Already there. 9, 10, 11. Come here. 12, 13. What's the last one? Uh-oh. Did I get it all? Oh, wait, this one needs one. This one needs to go right there. How cool is that?
Terrible.
I love that, man.
Just so yellow.
Big yellow one's called the sun. Huh. Can we define that there's 14 diagonals? 1, 2, 3, 4. I had 4 that came off of here. 1, 2, 3, 4, 4 that came off of here. How many exclusive ones? I already have one. There's 1. There's 2. There's 3. So that's 8, 9, 10, 11. Already counted. Exclusive one. There's 2 more. And then 1, 4, 4, 8, 9, 10, 11, 12, 13, 14. 14 diagonals. They're all exclusive. Oh, that's pretty cool. That makes my mind kind of work weird. It all looks like a big old yellow bunch of y'all that are sitting further back. Y'all up front are doing well. Well, let's move off this and get to the past. Counterexample. A specific case that shows a conjecture is false. So a conjecture that if x squared is always greater than x for all values of x, the counterexample would be if I were to have x equals 1/2, that means that 1/2 quantity squared is 1/4. So it's 1/4 greater than 1/2. So this is a counterexample. But sometimes when you look at that, going, well, of course x squared is always going to be greater than x. If you're talking about a whole number. As soon as you throw a fraction in the mix, it's going to change the game plan. Make sense? 1? Well, yeah, 1 wouldn't work. Why wouldn't 1 work? Because 1 is equal to 1, and 1 isn't just greater than 1. So x squared is not greater than x in this particular scenario. And in the scenario of values of 1 and less than 1, between 0 and 1, or fractions. To show a conjecture is true, you must prove it is true in all possible cases. To show a conjecture is false, you only need to show one counterexample. Okay? To show a conjecture is true, you must prove it's true in all possible cases. To show a conjecture is false, you only need to show one counterexample. Yeah. We're getting to proving, yes. We're getting there. It's good stuff. Give a counterexample for each of the following conjectures. All right. Here be the first one. Conjecture. The sum of two numbers is always greater than the original numbers. What's a counterexample? The sum of two numbers. What kind of numbers? Numbers. So if I add 2 and 3 together, that's greater than the original. Yes? Well, what happens? Do what? If negative, I go -2 plus -3, I get -5. Is that a counterexample? So, can we say the sum of two numbers is always greater than the original numbers? No. Just thinking of a simple case of two negative numbers being added together, or a negative number and a positive number. That could happen too. Conjecture. If a quadrilateral has 4 congruent angles, then it is a square. What does a congruent angle mean? What does a congruent angle mean? Equal. So, a quadrilateral is a 4-sided object. So if I have 4 congruent angles, so if they were all 90 degrees, that makes it a square. Agree? Oh, wait, we got a rectangle to throw into the bunch, don't we? So we have a counterexample. Conjecture. The square root of a squared plus b squared is equal to ab. Square root of a squared plus b squared. Well, let's take, I don't know, 7 and 10. And we'll square them. So that's 149. What's the square root of 149? 12 point something. But if I take 7 and add it to 10, I get 17. So is 12 point something and 17 the same number? No, we just showed a counterexample not even working that hard. This is cool stuff. I love this stuff. Hey, come on in. Guys, hide your dope weed.
Wow.
Everyone just realized, wow, there's a police officer in here.
I was wandering down the hall and I heard somebody scream.
Numbers. It's got to be me. See, I always have the door open. I am crazy. You guys don't know.
I gotta go write a report, or I would love to stay for a minute.
I was gonna get to the whole O.J. Simpson thing though.
You knock yourself out.
They'd probably, they already have my sense of humor. Guys and girls, what kind of sense of humor do I have?
The best one.
Ever.
Sick. What's
Twisted.
twisted? I laugh when what?
Someone falls.
There, tell.
Someone falls.
It's not even
See, she's got the same sentence. It's great. See you soon. All right. Can you make a conjecture? Oh yes, and I was recording then, so yeah. Yes.
Oh,
All right.
don't cut that out.
Heck no. Why would I do that? Can you make conjectures about even and odd numbers? The sum of two even numbers. The sum of two even numbers. What's an even number? 2,
2,
4,
4,
6,
6,
8.
8, 10.
So if I add two even numbers together, say like 8 and 20, I get 28. Is 28 even?
Yeah.
Okay, so can we say that the sum of two even numbers?
It's always even.
Can anyone think of a time when it's not? Can we do it? Say that?
Yeah.
What about if I went like 8 and 8? That's 16. Well, okay. I like that. I'm with it. All right. The sum of two odd numbers. What's an odd number? 3 and 3 and 5. 3 and 5. Add 3 and 5 together. I get 8, which is
Even.
Ooh. Ooh. What do you think? Can we say this?
No. Hold on. Oh, no, you're right.
Would it work? So like if we pick like 21 and 37. 21 and 37 is 58. Good. We got an even number though at least. I don't know, I kinda like that. The sum of an even and an odd number. Oh, we're gonna get this. If I add 3 and 10, I get 13. 3 and 8, I get 11. Is it always odd? The product, what is product? Multiplication. Multiplication. If I multiply two even numbers together, hold on. 10 and 12, I multiply those together, I get 120. What do you think? The product of two odd numbers, 3 and 7, is 21. Ooh.
21.
What about 5 and 9? 45. So the product of two odd numbers is always odd? Maybe? I don't know. The product of an even and an odd. So 4 and 5 is 20. What about product of an even and odd? Even and odd gives us always an even?
Yes.
2 and 3? 6. 2 and 7?
14.
2 and 9? 18. Is always what? Even? What do you guys think? Always even? I don't know. I mean, until you find a case against, right? Until you find a case against, they've got to be true. Do these statements all seem okay? Now, do you think that there's some weird scenario where it's like, okay, if I pick like 387 and 286, something different might happen? I don't know. I guess we could go through the infinite amount of numbers. What do you think? Is there more on this page? There might be. Nope. We got more notes. Okay, this one's done. Hey, Ann, it's coming. Say freeze on the board now. Yeah, it does. Sweet. Okay. So there's some things that we could say, this works. There's some things that we say that this works. What if I were to tell you this? If you had 1,000 lockers all in a row in a hallway, you still with me in this story? Still with me? And you had 1,000 students waiting in a line, and you went to the first person. I want you to go through and close every locker. Still with me in the story? And then the second person comes up and said, I want you to do the opposite to every second locker. Still with me? So if the locker's open, they close it. If it's closed, they open it. Still with me? And then the third person you go to and say, I want you to do the opposite to every third locker. Go to the fourth person, you say, do the opposite every fourth locker. Go to the fifth person, say, I want you to do the opposite every fifth. Until you get to the 1,000th person. So whatever place in line that person is, I will tell you that there is a total of this many. I said closed, right? There is a total of 31 lockers that would be closed by the time everyone got through. You got to tell me which 31. But don't do that yet. That's bonus for you guys later. All right. So, Chapter 2, Section 2, Conditional Statements. Develop an understanding of conditional and biconditional statements and the inverse, the converse, and the contrapositive. Statements associated with them. Guys and girls, this is how computer programming's basic fundamentals, once you got past the binary code, started to work. Okay? And this is how it continues to work, is this type of thinking, using if and then. This is a huge portion of mathematics that is really just having something called truth tables. Okay? And then we don't always have a statement that we use. Sometimes we'll just use the letter P and we'll use the letter Q. Okay, so let's kind of start walking through these a little bit. What do we got here? Conditional statement. A type of logical statement that has two parts, a hypothesis and a conclusion. If today is Friday, then tomorrow is Saturday. If today is Friday, then tomorrow is Saturday. What do you think? Sound good? If today is Friday, then tomorrow is Saturday. A typical logical statement that has two parts. A hypothesis. If I said if today is Friday, that would be our hypothesis. Then tomorrow is Saturday is our conclusion. If the measure of angle A is 90 degrees, then angle A is a right angle. This is our hypothesis. This is our conclusion. Hypothesis to conclusion. Still with me? Can I move on? All right. Okay, so hypothesis. The if part of a conditional statement. If you do your homework. If you do your homework. Conclusion. The then part of your conditional. Then you may play video games. Woo!
Why are you so loud?
I'm sorry, man. I had like 9 cups of coffee this morning. Hey, how are you? Did you see any surgeries this last week? Oh, okay. See you soon. Student took my med class who's been shadowing doctors like crazy. She was actually saw a surgery. The guy died. Not the doctor, but the patient.
That was scary.
She was cool. She was like, yeah, I think I died. She was like, just told him, like, are you okay? Yeah, I'm fine. All right. Let's see. If-then form. The form of a conditional statement that uses the word if and then, quote unquote. Then the if part contains a hypothesis, and the then part states the conclusion. Cats are mammals can be written as if an animal is a cat. Okay, then it is a mammal. Okay, cats are mammals. I could say if an animal is a cat, then it is a mammal. Sound all right so far? The converse. The converse is a shoe. You are absolutely right.
Boom.
The statement formed by exchanging the hypothesis and the conclusion. You change your if and your then statements. You keep the if there and you keep the then there, but you just flip-flop your information. The converse statement below. If angle A is a right angle, then the measure of angle A is 90 degrees. If measure of angle A is 90, then angle A is a right angle. So notice, they flip-flopped our if statement. They took if, the measure of angle, they took this here, plugged it in front. They took this if statement and made it your then statement. So your converse is you're flip-flopping your if and thens. You're leaving it as if and then, but you're changing it. So my original statement when I said if today is Friday, then tomorrow is Saturday, the converse of that was if tomorrow is Saturday, then today is Friday. That's the converse. And it is also a shoe. The inverse. The inverse, a statement formed by negating the hypothesis and conclusion of a conditional statement. So if today is not Friday, then tomorrow is not Saturday. I used the not in there. Inverse of the statement below, if measure of angle A is not 90, then angle A is not a right angle. So if measure of angle A equals 90, then angle A is right angle. So if I wanted to create the inverse of that, if we wanted the inverse of this statement, notice I removed the knots to go here. If I wanted to go from here to here, I put the knots back in. Okay? Almost done. Contrapositive, the equivalent statement formed by negating the hypothesis inclusion of a converse and conditional statement. So originally I said if today is Friday, then tomorrow is Saturday. Okay? If I say if tomorrow is not Saturday, then today is not Friday. There's my contrapositive. The equivalent statement I formed in negating the hypothesis and conclusion of the converse and the conditional statement. Contrapositive statement below. If angle A is not a right angle, then angle A is not 90 degrees. If measure of angle A is 90 degrees, then angle A is a right angle. So we got rid of the knots. Or I would put the knots back in. So the contrapositive, you flip-flop your if-thens and you put knots in there. What happens if you have not? If you say, hey, I'm not going to take out the trash today, what are you really going to do? You're going to take the trash out. So the not, you negate. I don't recommend talking to your parents that way. I'm not coming home tonight. What? You're grounded. Negation, the opposite of a statement. The ball is red, the negation, the ball is not red. Equivalent statements, two statements that are both true or both false. A conditional statement and its contrapositive are equivalent statements. If your statement is true, your contrapositive will always be true. If your statement is true, then your contrapositive is true, always. The inverse and the converse don't have to be. And if today's Friday, then tomorrow is Saturday, might not be the best statement. That might go with everything being true, which is called something called a biconditional statement, which we'll get to. Oh, when the conditional statement and its converse are true, the statement that contains the phrase if and only if, and we refer to that as IFF, not because we can't spell, it's because we're lazy. Two lines are perpendicular if and only if they intersect to form right angles. Important. All valid definitions can be written as biconditional statements. If you stated something that is completely valid, then you can be written as a biconditional statement. If it's biconditional, you use the term if and only if. Am I on the back page of the notes? Sweet. Everyone's still doing okay? And I know I'm kind of covering a lot. I'm trying to be happy and motivated, and I'm excited. This stuff is fun. I'm telling you what, there's a math class you can take. It's all this stuff. It's the best math class. You're like, dude, you're sick. Yes, I am. Two lines that intersect to form a right angle. So this is perpendicular lines. Two lines that intersect to form a right angle indicated by an upside down T. So when we do perpendicular lines, we use the upside down T or an upside down L in a diagram. Okay? Which is this. Perpendicular lines. Two lines are perpendicular if and only if. Use IFF. They intersect at right angles. Do these lines intersect at right angles? They're perpendicular then. A rabbit is a mammal. What's the conditional statement? Here you go. Agree? If an animal is a rabbit, then it is a mammal. What's the converse other than the shoes? What's the converse? If an animal is a mammal, then it is a rabbit. Is this always true? No. Not always true. What's the inverse? How do I write the inverse? If an animal is not a rabbit, if an animal is not a rabbit, then it is not what? A mammal? Again, not always true. The contrapositive is the negation of the converse. If an animal is not a mammal, then it is not a rabbit. Is this a biconditional statement? Are all four terms 100% true all the time? No, it is not a biconditional statement then. Biconditional means that the statement, the converse, the inverse, and the contrapositive are always true. It's the only time you can say if and only if. Okay? A good one to go with, again, is if today is Friday, then tomorrow is Saturday. You can go through and make that, and you can make that a biconditional statement. If I made it a biconditional statement, I could say, today is Friday, if and only if tomorrow is Saturday. Make sense? Today is Friday, if and only if tomorrow is Saturday. Okay. For your statement, do the following. Write a fact as a conditional statement. Write the converse and decide if it is true or not. Write the inverse, decide if it is true or not. Write the contrapositive and decide if that is true. If the statement is true, then the contrapositive has to be true. If it would be valid to write a biconditional statement. Okay, so I asked you guys and girls to start 2.1. Let's have 2.2 done. Remember that sentences have periods and start with a capital letter. Oh, okay. Glad we can put that in there for you. I can't believe I knocked that whole 2 lectures, 1 period. Woo! That's awesome. Yeah.
How did you figure out that logic thing?
Yeah, we